All right, we are going to take a look at calorimetry and calculations associated with calorimetry. So we will take a look at how to find a couple of different types of calorimetry situations or calculations. So we're going to look at heat transferred between objects or substances. So this might be like between a piece of metal and water. We're going to look at heat transferred during a chemical reaction and heat transferred when a solution is formed. So when we're forming that aqueous solution, dissolving something in water. So each of these is dealing with kind of a different lab type situation. So what is calorimetry? Calorimetry is the measurement of heat transfer. It is a lab process similar to how we've talked about titration as a lab process. A calorimeter is a device used to determine the amount of heat transferred between things, between any of those examples we looked at on the first slide. Typically, a polystyrene container is used due to its ability to insulate. So you might know it as styrofoam, the brand styrofoam, but it's made of polystyrene, so you might see either of those names. So it's a pretty basic lab setup, and we use that because the styrofoam because it will insulate, keep all the heat in, so we can trap it and measure it. The deal with heat flow is it cannot be measured directly. We do not have a device that measures heat. So we have to measure temperature change before or during our situation, so before and after, and use that to calculate heat. So we're going to go back to our Q equation, our specific heat equation. So the equipment looks like this. So we have our styrofoam cup. We have with a cover to keep all the heat in. We have water inside. We have some sort of stir. So that's what this part is. And then we have a thermometer. So for all types of calorimetry, we have water involved. The reason why is because we know lots of information about water, like we can find its mass, easily measure it, or volume. We know its specific heat. So water is, we're going to be using this a lot, 4.184 joules per gram degrees Celsius for that specific heat. So we are going to get very familiar with that value. And we can easily measure its change in temperature. So, and because it has this high specific heat, it takes a lot of energy to actually change the temperature of water. So we don't have to typically worry about the water evaporating or boiling away during our reaction, even if we're giving it a ton of extra energy. So we're going to be looking at how we determine our system and surroundings with this kind of setup. We call this basic one a coffee cup calorimeter because it uses, sometimes we use like styrofoam coffee cups. In our labs we use a bigger styrofoam container that we have with thicker walls, so it has good insulation and is a little more stable than the coffee cup. There's another type that you could check out in your textbook or online called a bomb calorimeter, B-O-M-B. And it's only a little different because it burns the sample of chemical in the process, but it's still transferring its energy to water and measuring that temperature change of the water. So not a ton of difference there. So what we want to look at is how we decide our system and surroundings in calorimetry. So remember, a system is the part of the situation that we're focusing on, and its surroundings, we want to look at its immediate surroundings so we can determine the direction of heat flow. So typically our system will be the reactants or products in a chemical reaction, or a chemical that we're dissolving if we're making a solution, if we're putting, say, a piece of metal in water to find the metal specific heat, the metal would be our system. Our surroundings in every situation is going to be water. And again, it's because we have its specific heat, it's readily available, and easy to use. So with the system and surroundings, when we look at a situation, we are going to be able to determine the heat lost or gained by the water in that situation and determine that it is equal to the heat lost or gained by the reaction. And the reason for this is the law of conservation of energy. So what that law refers to is the, tripping on my words here. So the law of conservation of energy states that energy cannot be created or destroyed. It can only transfer between things and change forms. So if we think about our calorimeter, go back to my previous picture here. If we put something like a piece of metal inside our calorimeter, then if the metal gains heat from the water and the heat goes in, then however much heat the water lost is the same amount that the metal gained. Is that law of conservation of energy. They're just transferring between the two. So that law is going to help us out. So what does this mean in terms of values? If we're able to find the Q, or the heat of our water, and it's calculated to be something like positive 568 joules, let's just say, then the water gained heat because it's positive. And this means the reaction transferred heat to the water, the reaction or whatever the chemical or situation was that was giving away the heat, it transferred it to the water. So our reaction or situation is exothermic, and Q of our chemical reaction would be negative 568 joules. So they're the same value, it's just that the water gained the energy and the reaction lost the energy, but it's the same amount. So this idea is going to allow us to actually do our calculations and find out the heat of a reaction, or the heat formed when a solution is made, or when chemicals or substances are just exchanging energy. So let's take a look at our first example here. So placing metal in water. This is a very common type of lab situation, and each of these is going to be more of a lab type situation. So they're a little more complex in terms of their problems. So keep that in mind. Don't get too overwhelmed here. So it says a 10.5 gram piece of aluminum is heated to 258 degrees Celsius and placed into the calorimeter, containing 200 milliliters of water at 22.5 degrees Celsius. The highest temperature reached by the water is measured at 41.4 degrees Celsius. What is the specific heat of the aluminum? So if we just think about this particular situation, we've got water in our calorimeter. We've placed a piece of aluminum into the water. And we want to see just to kind of clarify which direction the energy is going. So our piece of aluminum is at 258 degrees Celsius and the water is at 22.5. So already our metal is much hotter than our water. And our water heats up to 41.4. So that means that the water is receiving energy. So we would have our arrow going from our system, the aluminum, to our surroundings, the water. So if we were thinking about our Q values, the Q of the water would need to be positive, so it's positive something joules, and our Q of our aluminum would have to be negative because it's losing energy. But these two values are equal to each other. So if we can calculate one, we can find the other. Now our goal in this question is to find the specific heat of our aluminum. So we're going to look at how we actually calculate this answer here. So same question. So we're going to start breaking down this information. The easiest way, on your paper it has the steps written out. So it does say to find your heat of your metal, or excuse me, of your water first. So before we do that though, let's just list out all of our information and see what we have so that we can see why we're going to start with the water. So our equation is the same one we've been using, Q equals mc delta T. So we're going to list out our variables there. So we're going to do Q, M, C, and delta T. And we're going to focus this list on water. Okay, so looking at our information here, we have that our metal is placed in 200 milliliters of water. And anytime we're dealing with water or an aqueous solution, we know that water's density is 1 gram per milliliter. So if you're measuring out 200 milliliters, that's the same as having 200 grams of water. They're equivalent to each other. And that water is starting at 22.5 degrees Celsius. We have the highest temperature reached is 41.4 degrees Celsius. So we can do our change in temperature, 41.4 minus 22.5. And I calculated this earlier at 18.9 degrees Celsius, but you can always check it. It's a good idea too. The other value we have, as I mentioned before, we're going to use a lot, is our specific heat of our water. So the 4.184 joules per gram degrees Celsius. So we have a significant amount of information about our water right now, but let's check out what we have for our metal, which is aluminum. So Q, M, C, and delta T. So taking a look back at our question, we have that our piece of aluminum is 10.5 grams. We know that it starts at 258 degrees Celsius. And something we have to infer in this question, and we can in most of these questions, is it says that the highest temperature reached by the water was 41.4 degrees Celsius. Now, the rule with temperature changing, when you're putting two things together, they will exchange heat until their temperatures are the same. So we can assume that this final temperature of the water is the same final temperature for our metal. So 41.4 minus 258, and we get negative 216.6. And we'll end up rounding later in the question so we can have a better answer here. Our question is asking for the specific heat of our metal, so that's C, so we don't know that part. So looking at these two situations, we don't have heat for either of them, but for the metal we also don't have its specific heat. So we can't do any calculation for the aluminum right now, but we can calculate for the water. We can find the amount of energy that the water is giving off or taking in. So our Q for our water, and you can always give a label to your values as a subscript, is going to be its mass, 200 grams, times its specific heat, times the change in temperature. And we can find that our Q of our water, if you want, you can pause and calculate, make sure you're on the right track here. You should get 15,815.52, but we want to round that. We have 4 sig figs, 4, and then 3, so we want to round off to 3. So 15800, and our units cancel, our grams and our Celsius cancel. We are left with joules. So this is the amount of energy that the water gained. It is positive. So it's the water is taking in that heat as we looked at in the heat flow diagram. So now what we can do with this is, since the water gained this much heat, that means that our metal had to have lost this much heat. So we are going to put the same value but make it negative for our metal. Now we can actually solve for the specific heat of the metal. If we rearrange our equation, to get C by itself, we would have to divide by M and delta T on both sides. So our M and our delta T cancel. So C is equal to Q over M delta T. C is equal to, so our Q value, negative 15800 joules, over 10.5 grams times negative 216.6 degrees Celsius. So if we calculate this out, notice we do have a negative over a negative, so we should get a positive value. C has to be a positive value. So I got 6.95 joules per gram degrees Celsius, because none of our units cancel. Check your work, make sure you get the same answer in your calculator. Make sure you're putting it in your calculator correctly. This is, sometimes students get everything correct on their test, but they just put it in their calculator wrong, and so I want to make sure you guys are doing it right. So this would be our final answer. We can see that we can always analyze a few things, like our Q of our water was positive, so that would be endothermic. For our metal, it's exothermic because it's negative. We could also show that we're using the law of conservation of energy because these two values are the same as each other. So we're going to take a look at another situation. So that's calculating when we're just putting a metal or object in water. Our next situation we're going to look at is adding together aqueous chemicals to react. My thing is not quite wide enough to see that, so react. So our question here, let's read through it, and then we'll take a look at the calorimeter setup. A 75, actually I believe I changed this value on your paper, so I didn't change it on mine. So I changed it to 400 milliliters. There we go. So a 400 milliliter sample of 0.05 molar hydrogen peroxide, H2O2, is reacted with 100 milliliters of 0.2 molar potassium permanganate, KMnO4, solution. Both solutions are at 19 degrees Celsius. The highest temperature reached by the reaction is measured at 37.4 degrees Celsius. What is the heat of reaction, or delta H reaction? Oh, I believe I actually skipped, I feel like I skipped something with you guys. I did, and I don't have it printed. It's on your note sheet. Let me check it. So there is one slide, or one thing before this. So on your note sheet, it does point out that Q of the reaction and delta H of reaction. So your Q of your reaction is your heat lost or gained by the reaction or by an experiment. And the only difference for your delta H, so delta H is enthalpy of reaction, and the heat, it's the heat lost or gained by the balanced chemical equation. Balanced reaction. So Rxn is reaction. It's just a shorthand for it. So the only difference between these is Q is found with Q equals MC delta T. Delta H, we can use Q, and we just have to do an extra calculation. So delta H of the reaction is equal to Q of the reaction divided by the moles of one of your chemicals. Sorry, that's like scooting off the edge. So if we find moles of one of our chemicals, we divide these two values, and it gives us our enthalpy of our reaction. So we're going to take a look at the difference in this. Sorry, so back to our question. So we're finding the delta H of reaction. So let's think about this situation. We've got two chemicals. So say we have our chemical over here. It's the peroxide, and we're going to pour that in. And then we've got our potassium permanganate, and we're going to pour that in to our calorimeter. We're going to mix them together. So we're going to have the 400 milliliters plus the 100 milliliters added together. So we're going to have a total of 500 milliliters of solution. And those two chemicals are going to react with each other. Now both of them are dissolved in water. So you've got these chemicals, the potassium permanganate dissolved in some water and the H2O2 in some water. So you're not just adding chemicals together, you're adding water. Now the water is not part of the reaction. It doesn't change at all. So the water is just hanging out and it's allowing the chemicals to mix with each other. So we can still create our system and surroundings. Our system is going to be our chemicals dissolved or reacting in the water, and our water is going to be the surroundings. So if we thought of our chemicals or our reaction as the system, and then our surroundings is the water, we can look at what's happening here and see which direction the energy is going. So our overall solution, the thermometer is measuring, it's going from 19 to 37 degrees Celsius. So that means it's the water, the solution is going up in temperature. This is going up. So the water is gaining energy from the reaction. Okay, so if this wasn't in a styrofoam container, it was like in a beaker, we would feel it, the beaker, and it would feel warm to us because it's giving off that energy and heating up. So that means that our Q for our water is going to be a positive number of joules, and our Q for our reaction is going to be a negative number of joules. And again, those two values will be the same as each other. So let's look at how we set up the problem here. Oh, I need to get it all in the view. Okay. I think it's only cut off just slightly. So again, I changed this to 400. Sorry about that. And this is supposed to say adding aqueous chemicals. I obviously printed these before I got all my edits done. So let's talk about, we're going to set up our data kind of like we did in the first one. So let's start with all of our information about our water. So we'll start with Q of water. It's all going to be like our list of water. Our mass, our specific heat, and our change in temperature. So again, our specific heat, always the same, 4.184 joules per gram degree Celsius. We have our change in temperature of the solution. We go from 19 to 37.4. So final minus initial. And we get a total of 18.4 degrees Celsius. Again, you can always pause and check the answers before I give them. Now, our mass. Remember, each of these are aqueous solutions, so they're dissolved in water. So most of your mass is coming from the water itself. So if we look at our peroxide, we've got 400 milliliters of peroxide, 100 milliliters of permanganate. So we are going to add those two values together since they're being poured together, and we get a total of 500 milliliters. Now remember that our density of water is 1 gram per milliliter, so we can just change the milliliters on this to grams. So right now, just looking at our list here, we've got enough information to find out how much heat was gained or lost by that water. We know in this situation it's going to be gained. So let's go ahead and calculate it. Q of our water equals 500 grams times our specific heat times our change in temperature. So our Q of our water is equal to, multiply all these together, you should have, we have 4 sig figs here, 4 and then 3. So we get 3 sig figs, 38500 is what I got, joules. So that is our amount of energy gained by our water. Now, in your steps, it says find the heat gained or lost by the reaction, so Q of the reaction. So our Q for our reaction, remember, is just the same value, but we're going to make it negative. So we have that value. So the second step is just flipping the sign and making sure we record that. Now, we want to find, in this case, the change in enthalpy of the reaction. So this is a little different than the metal in water. We want to find out how much heat was gained or lost in the reaction itself. So chemical reactions are always based on the mole ratios and the moles of the chemicals. So the next thing we need is to find out the moles of one of our chemicals. It does not matter which one. When they set up these type of questions, you're always going to have the correct mole ratios given. So you just have to calculate one. So if we picked the peroxide, we would have the volume of the peroxide and we have its molarity given. So volume and molarity can always be related together using our lovely molarity equation. So we have the molarity, we can get liters, we can convert our milliliters to liters, and that will allow us to find moles of our chemical. So to rearrange this, our moles equal our molarity times our volume. Our molarity of our permanganate is 0.050 molar times the liters, so 400 milliliters, divide that by 1,000, you get 0.4000 liters. Keep all those sig figs. Oops, I'm sorry, we can't see that. There we go, camera adjustment. All right, so our moles of our permanganate is 0.02, and we have two significant figures, so we need that extra 0. Moles of our chemical. So now that we have our energy gained or lost by the reaction because it's negative, we know how many moles of our chemical reacted. Now we can find the change in enthalpy of the reaction. And all that is your Q divided by your moles. So negative 38500 joules over 0.020 moles. And our delta H of our reaction is negative 1900. Sorry, not 1900. 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5. 1,900,000. Sorry. Joules per mole. Now, when you get these very, very large numbers like this in your joules, you can always convert them, and we're going to start to see it later in this unit as well. You can convert them to kilojoules per mole. So if we were to just convert that, we divide by 1,000 to get to kilo. So it would be negative 1,900 kilojoules per mole. And we will really commonly see our values written in kilojoules because the values just get very large. So that's how we find our heat of our reaction. A little bit different process. We're only using the Q equation, the specific heat equation, once in this, but then we have to do an extra step to find our heat of our reaction. So this is our final answer here. So we're going to look at one more situation. Let me get set back up here. Sorry, this video is so long, but I want to make sure you guys get all these examples. So, our last example is creating an aqueous solution. So, dissolving a salt into water. So, a 15-gram sample of ammonium chloride, I don't know why it says of twice, NH4Cl is put into the calorimeter containing 300 milliliters of water at 25.5 degrees Celsius. The highest temperature reached by the solution is 39.2 degrees Celsius. We want to find the enthalpy of solution. So this is the same as our enthalpy of reaction. We just label it a little different because it's not a reaction. We're just creating a solution, dissolving. So different label, same process. So if we look at this, we've got our temperature increasing. We do in all of these right now, we've had temperature increasing, so that's kind of a common thing. but you will see some in your homework where it does decrease. There are examples like that. So our temperature goes from 22.5 to 39.2 degrees Celsius. So if we think about our situation, we're adding the ammonium chloride into the water. So our NH4Cl is going into the water. It's dissolving and breaking up into its ions like that. So that chemical, those chemicals would be our system, and our surroundings would be the water. So since our temperature is increasing of the solution, our energy would be going to the water, so it would be exothermic. So our Q of our water would be a positive value, and the Q of the solution, since we're making a solution, would be a negative value. So let's take a look at how we calculate this last one. All right, so let's start with our Q again of our water. So Q equals M equals C delta T. So we do have our mass of our water because we have its volume. So 300.0 grams of water. We've got our specific heat of water as always. And we can find our change in temperature. So we've got 39.2 minus 22.5, and we get, check it, and we get 16.7 degrees Celsius. So like our other problems, we can go ahead and find our Q value of our water, 300 times our specific heat, times our 16.7 degrees Celsius, delta T. Go ahead, pause it, and calculate it and check your answer. So we should have gotten, I'm just going to check my answer one more time. There we go. So we should have gotten 20,961.84. But we have 4, 4, and 3 significant figures. So 200 and the 9 would round. So 210,000 joules. All right. So that is our heat of our water. So that's how much heat the water gained. Now what that can allow us to do is find out how much heat the solution or their chemicals gave off. So we take the same number and make it negative. And let's just keep in mind that this does have 3 significant figures based on our values. So we'll use that to help us at the end to find our sig figs. So we want to find the enthalpy of our solution. So to find that, again, we need our Q and we need our moles of our chemical. So we were given 15 grams of our ammonium chloride. So we can change our grams of ammonium chloride to moles. And we do that with a straight railroad track conversion. So you can calculate your molar mass of ammonium chloride. You should get 53 let me just check that. So 14.01 for our nitrogen, plus 4.04 for our hydrogens, and 35.45 for chlorine. So 53.5 grams per mole. So we would have 0.280 moles of ammonium chloride. So now our last step is to find our enthalpy of our solution. So how much heat is gained or lost per mole of chemical that's dissolved. So we're going to take our heat, Q, negative 210,000. We're going to divide it by our moles, 0.280 moles. And we get negative 210,000 by 0.28. We get negative 750,000 joules per mole. So again, since we have such a large number, sorry, it's running off the edge of the paper. We can convert it to kilojoules. It's very common. So that would move that decimal 3 times or divide it by 1,000. So negative 750 kilojoules per mole. And that is our heat of our solution. So we've kind of got two main type of calculations we can do here. We have them where we're going to use our every single calculation is going to start with Q of your water, and we're going to find that first. Then, depending on the situation, if it's like the first example with a metal, we will use our Q of our water to find our Q of our metal, and then use that specific heat equation again to get to our specific heat of the metal. Or if it's a reaction or a dissolving of a solution like this one, we'll change to our Q of our reaction or solution by making the value opposite sign. Calculate moles depending on what they're giving you, so either from grams or from molarity, and then divide the two. So all of these processes have similarities. The big thing is to keep track and pay attention in the question to what value belongs to what substance, and be careful in assigning those values to different substances. If you have questions, let us know in class.